and I didn't have time to discuss it. I mean, we think they're very representative because they show up in these stocks. Now the stocks are a selection. I mean, not all rotation curves we have at high redshift are equally good, and we have to model, so we can only take about a third, but this falling curve for the stock had 100 galaxies in it. Yeah?
One more.
Go ahead and take me.
A couple comments. First, the galaxies that we're looking at high redshift typically are quite compact, and so if you compare an actual kiloparsecs to the galaxies today, it's not as discrepant. Secondly, the measurements are all being made with the emission lines, which include a complex mixture of whatever perturbances, et cetera, and it's not virialized fully in these distant galaxies. So I think that may also affect what we conclude in terms of the Vmax.
Yeah, so I mean, certainly perturbations play a big role, absolutely. And so in this work, I see this as this work will undoubtedly go forward. People will, as in the low redshift universe, pay attention to, of course, edge-on systems and then making sure there are no neighbors. In the 5, 2 have one neighbor on one side, but you have the other side, and the falling rotation curve is symmetric. So that's very important characteristic. There will be the issue of warps. Now it's less likely to have warps at high redshift because of the high velocity dispersion, but all of this will have to be tested. I'm with you. This is early days, but I believe it's a new field which will come forward.
If there are no further questions, let's thank Reinhard again. And now we have Sandro Tekele, growth of bulges and disks on the star-forming main sequence.
Okay, hi everyone. So we are going to look through the dust, trying to understand how the bulges and disks in star-forming main sequence galaxies are growing. And the work I'm presenting has been done in close collaboration with many people. I would like especially to highlight my PhD advisor, Marcella Carolo, but also Natasha Förster-Schreiber, Alvaro Renzini, and Avishai Deckel. So the galaxies I'm presenting have already been partially introduced by Reinhard before. These are part of the Symphony ZSynF AO program. So these are galaxies that lie on the star-forming main sequence at redshift of 2. You can see they cover a wide range in stellar mass and star formation rate. But the main selection criterion for these galaxies was really driven by the observability of the H-alpha emission line. And so what we try to do is that they lie more or less on the main sequence. And as you can see, we are talking here about 35 galaxies. So we don't have the huge samples of about 600 galaxies. But what we try to do is to zoom in on those galaxies. On one side with HSD, so we get a handle on the stellar mass distribution in those galaxies. And also with Symphony, we get a handle on the H-alpha emission line and therefore on the instantaneous star formation rate density within the galaxies. And I would like to highlight, this is really the AO sample, so we have adaptive optics, so we are able to trace these distributions in these galaxies on about 1 to 2 kiloparsec at redshift of 2. And so last year we published a work where we looked into the distribution of the stellar mass and the star formation rate density, here going from lower masses, so a few times 10 to the 9 to 10 to the 10, up to higher masses of the order of 10 to the 11 solar masses. And in red it's shown the stellar mass density profiles. And you can see when you go from lower to higher masses, you not just increase the overall normalization, but you're also increasing the central concentration. So here you can describe the galaxies well with a Cerseic index of about 1, whereas here you are more in the Cerseic index regime of about 3. And these are still star-forming galaxies on the main sequence at redshift of 2. Now, another interesting thing, of course, is when you look at the star formation rate distribution, and actually those are well described by exponential disks throughout the stellar mass range here we are looking at. If you want to understand now where they are growing, and especially where they are changing the stellar mass density profile, you can look at the specific star formation rate distribution within these galaxies. And so what I'm showing you here below in black and gray is the star formation rate surface density divided by the stellar mass surface density. So you get the specific star formation rate profiles. And you can see that in the low and intermediate mass ranges, those are more or less flat. And so this implies that you are doubling your mass in the center and in the outskirts, more or less hand in hand. So they are growing in the centers and in the outskirts, more or less with the same pace. Now, when you go to higher masses, you can see that the specific star formation rate profile is actually rising towards the outskirts. And so you have about an order of magnitude, lower specific star formation rate in the center than in the outskirts. And so when you look into the number, this corresponds, when you look at the inverse of the specific star formation rate, so the mass doubling time scale roughly, this is of the order of about 10 gigayears, and this is longer than the Hubble time at redshift of 2. So although these galaxies are still star forming in their center, so they're making stars, the stars you're making are not really contributing anymore to the overall stellar mass, which is already there. So we can talk here about the heavily star-forming outskirts and more or less quiescent centers. Now, to drive those star formation rate density profiles, we had to assume something for the dust attenuation. And so we didn't have a good handle on that in this work last year. And so what we assumed is something very simplistic. We just assumed a constant dust attenuation throughout the galaxy. And this might be too simplistic because you can see that the star formation rate, but also the stellar mass density profiles peak in the center. So probably also the dust attenuation should peak in the center. So it's a very valuable question whether this reduction of the specific star formation rate in the center is driven by really a less star formation activity, or whether this is driven by a dust attenuation effect. And so we went back to the telescope, capitalizing our previous data, and we got another 43 HSD orbits where we really traced the B and I band imaging to get a handle on the UV continuum slope. The B and I band image trace the rest frame far UV and near UV, and so we can get a good handle on the dust attenuation, again resolved in those galaxies. In addition to this, we get another star formation rate tracer, so we can now not just use H alpha, but actually also the UV as a star formation rate tracer. So for the next few slides, I will be really focusing on the dust attenuation, the stellar mass density, and the star formation rate density within 10 main sequence galaxies at the spatial resolution of about 1 to 2 kiloparsecs. And so let's go straight to the dust attenuation profiles. So this is measured in the visual band. You can see here the individual profiles. So these are the black curves, and the median profile is shown you as a green line. And the first thing to notice is that there's a large variety of profiles. Okay, so we have galaxies that have really, which are peaking very strongly in the center. So we have really dust-obscured centers, for example, for this galaxy here. But we have also other galaxies that are more or less flat or even a bit decreasing towards to the center. And another second effect, if you look at the average profiles now, you can see that, of course, as expected, they're really increasing towards to the center, consistent with previous studies, for example, by Stein-Witz, where they did a resolved SAD analysis, and they were mentioning already that they measured a dust attenuation in the visual of about 0.7 magnitudes outside of 2 effective radius. And this is really key feature, actually. What we see is not just the centers that have a lot of dust, but actually when you go to the outskirts, we measure a substantial dust attenuation also out to 10 kiloparsec of up to about 0.5 magnitudes. Now, if you want, so this is good to correct the continuum, so the UV for the dust, but if you want to now to go and correct H alpha for the dust attenuation, we need to get somehow a handle on how we can correct H alpha, because H alpha is coming from the nebular lines, and so we need to convert it to a gas dust attenuation. And so there are many different prescriptions. Here I list a few of them, for example, the Stein-Witz et al. From 2013. Then from the local universe, which is also used at high redshift, is the Calzetti one with F equal 0.44. So F is really telling you what the color excess ratio is between the gas and the stars. And the Cascino et al., which is 0.7. And at the moment, at least in literature, there is a huge debate about which factor is really the right one, and so you can see that there is large variation. What we still, whatever prescription you want to use, you still find a lot of dust still also in the outskirts. There was a recent study by Nelson et al. Who uses GRISM data from the 3D HSD survey. They're using a more direct approach. They're using the Balmer decrement in those galaxies, and they have to stack several hundred galaxies in a similar mass range like we are looking at to get a dust attenuation profile. What they find is that we find about similar dust attenuation in the centers, but they don't find any dust attenuation in the outskirts, which is the difference with our result. So we can now go on and ask a question whether we would be able to reproduce dust attenuation profiles also in the simulations. Now I'll show you here a very, very crude comparison, okay? So I'm talking here about the VLA simulations. These are cosmological zoom-in simulations, and I don't have really time to go into great details in them. I'm sure Avishai will also, and also I think Daniel Serino will be talking about this in more detail. But in those simulations, what I've done is I'm using a stellar mass and also as a redshift matched sample. I'm getting the gas surface density profiles of those galaxies, and then I'm just converting with a simple factor the gas surface density I'm measuring to dust attenuation profiles. I'm saying this is very crude, but overall we find actually quite good agreement with these extended dust attenuation profiles we measure also in the data. Now, again, maybe the key result and most interesting is when we now look at the growth of galaxies, again due to star formation, so we're looking at the specific star formation rate here from the UV and here from the H-alpha. The first thing to notice here is again that the blue and the red line showing you the lower or the intermediate mass galaxies between 10 to the 10 and 10 to the 11 and above 10 to the 11 solar masses. You can see that the UV and the H-alpha give you very consistent results. And so this is already very nice. Now when we use the dust attenuation profiles, which are centrally peaked usually, we indeed find a higher specific star formation in the center than what we would just infer from using the constant dust attenuation profile. And overall, but you see there's maybe a factor of 2 difference, but overall we don't find that it's getting flat. So even with these new attenuation profiles, we still find that the specific star formation rates are flat, and therefore the mass doubling time at all radius is more or less the same. For the low mass or the intermediate mass galaxies, and for the higher mass galaxies, we have these rising specific star formation rate profiles. So now, something else we were looking at, especially with Avishai here, is looking at in the simulations now how galaxies actually evolve about the main sequence, about the star-forming main sequence. And one thing we find is, of course, that the galaxies at high redshifts are very gas-rich, and so you can have a very small disturber, for example, a counter-rotating stream is already enough for a minor merger. That lowers the angular momentum of the gas disk, and a lot of gas gets fueled to the center. And so what you have is a so-called compaction event, where then you make a lot of stars in the center, which of course produce also outflows. So what happens actually is then you are reducing the gas surface density in the center again, and you're reducing your star formation activity. And usually what you are able to do is actually to replenish the gas disk again, because you're at high redshifts, you are able to reaccrete gas in a short amount of time, and you are able to form stars again, mostly in the outskirts. And so you can do this several times until you are successfully quenching. But one of the key features here is that above here you are producing most of your stars actually in the center, and when you are below the main sequence you are forming more stars in the outskirts. And so one thing we can do now with this resolved data from individual galaxies, we need to understand where they are lying about the main sequence, and then also looking into the specific star formation rate distribution. And so I'm showing you here the specific star formation rate in the center over the specific star formation rate in the outskirts, here using physical units and here using normalized units by the half mass radius. The blue line shows you simulations, and the points showing you H-alpha and UV measurements. And overall, it's quite nice. We see that galaxies that tend to lie above the main sequence in observations, they also have specific star formation rate values that are more or less consistent with being flat. So these galaxies have a ratio of about 1, and galaxies that tend to fall below the main sequence have specific star formation ratios that are below 1, and therefore having more specific star formation rate in the outskirts than in the center. Okay, so I think my time is up, and I can just go very quickly through the conclusions. So again, we measured the dust attenuation profiles, and we update now the star formation and specific star formation profiles in the individual galaxies. We find that galaxies below 10 to the 11 have more or less flat specific star formation rate profiles, and when you look at the values, they are about 3 per gigayear, so this is consistent with the main sequence actually throughout the disk. And you have a concurrent growth of the centers and the outskirts. When you go to higher masses, you have a specific star formation rate profiles that are rising towards the outskirts, which is consistent with the suppression of the star formation activity in the inner cores. Also, highlighted already by Reinhard Genzel with the morphological quenching, for example, or the inside-out quenching in our paper last year. Okay, thank you very much for your attention.
So I'm glad you thought about the H-alpha and H-beta and making sure to compare with that. I seem to remember Eric and Nelson also talking about trying to make sure that they reproduce the total amount of infrared flux that was coming out, because if you're extinguishing, you have to pay the piper, right? And then you can see the infrared flux coming out. And then I'm also reminded of a talk that I saw in April by some person whose name I forget, which is terrible, where they did ALMA imaging of some of these galaxies and saw very centrally concentrated emission, which they were interpreting as being very centrally
Yeah,
concentrated.
so
dust.
Guillermo Barro has a recent paper on this.
Exactly. So,
Okay.
How do your attenuation estimates? I mean, because they disagree with you about the suppression of specific star formation in the inner parts in the massive galaxies. So, what's your interpretation of those results? Is the issue still open, or do you think that you've taken care of?
Okay, so the first thing is, so the galaxies we are looking at, as Reinhard already mentioned, they are a bit bluer, and so they are not really the very dust-obscured objects, for example, which are studied by Guillermo. So these are really which are usually above the main sequence and really dust-obscured. If you look at for example, in the UVJ diagram, they lie really in the dusty regions. Ours are lying more in the blue regions. Now, I checked the infrared data from our galaxies, and we don't have the resolved infrared data, so we cannot really check it on the radial scale. But if I look at the integrated flux, I find very consistent information for the galaxies which are detected in the infrared. Now, a lot of galaxies are not detected in the infrared because they are just not star-forming enough or not dust-obscured enough. But I have an upper limit, and those are actually consistent with what I find from the UV. Yeah.
Let an old man remind you of the following. What's going to happen here as we get spatially resolved information in, obviously HST, integral field unit, and then ALMA, is that the knowledge or the findings of the UV sensitive and the infrared sensitive communities will drift apart like crazy. And that is very well known. That happened in a local universe. So I just want to warn people here. If you're talking about AV of 1, that's an equivalent screen AV, by the way. I pointed that out to you already. That could be AV of infinity in a mixed case. And in fact, the Barrow or Tadaki or whatever else nuggets there in the center have a beam averaged equivalent AV of several hundred. So heck, how can you possibly see any H alpha? Because it's not a screen. So you can actually see some amount of H alpha coming through. But and that's known from the ULERGs, and ARP220 comes to mind, and all these other things. If that column becomes too large, sorry, you won't see it in the UV in an extincted way. You just don't see it. And so then you may be fooled.
Again, on the
Anyone want to challenge that?
Well, actually, as I said, I agree with that we cannot, at the moment, get the infrared data resolved. But at least from the integrated perspective, those galaxies are not the heavily dust-obscured ones.
Any other questions? Short. Okay, let's thank Sandra again. And we have Sedona Price, Kinematics of Z2 star formation galaxies with MOSDEF, CANDELS, and MassiveFIRE.
I want to thank the organizers for giving me the opportunity to be here. It's the first time I've been to this workshop. So I'm going to be presenting work that I've done with Mariska Creek, the MOSDEF collaboration, and Robert Feldman and the FIRE collaboration. So first, to give you an overview, the MOSDEF